So we're going to talk today about UI. It doesn't say that in the title. It talks about spatial computing. I'm going to make a couple of assertions. And the remarks here, which I hope are brief, are structured as 2 counts. We're going to count to 4, and then we're going to count to 5. And when we're done with those 2 counts, you'll know everything that I know, which isn't very much, and then we'll move on with our lives. So the first assertion is that one of the highest leverage things that we can undertake, one of the highest leverage activities that we can engage in right now as computer scientists, as technologists, is in the field of user interface. Now, that's historically, or for the last 30 years, has not been a big topic. But it's not just because it's been ignored that we can get a lot out of working on it. It's also because enormous and sort of weighty initiatives like the field of cognitive computing are coming along, that they're going to demand a much more capable UI. We're not going to be able to get done what we want to get done if we're still mousing around and fiddling with the keyboard. So you can believe that or not, but I'm going to try to convince you over the next few minutes that that is indeed the case. Second, let's try this out. This is just a little bit of a kind of brain exercise to begin with. The next statement that you see is going to seem nonsensical, but it's worth digging in to try to figure out why it's nonsensical. What UI does your business use? Pure nonsense. Some years ago, you could have said, what OS does your business use? And that would have meant something. It doesn't really mean anything today, because OSs have essentially converged in their functionality, even though there are still a few discrete manufacturers that make them. But what UI does your business use? Well, this would have meaning if there were more than one UI. But we've been stuck for 30 years with that Xerox PARC, Apple Macintosh UI. We've still got it today. Now, it is certainly a testament to its longevity and its adaptability that it's still kind of hobbling along today. But again, we think we can do better. And then maybe this will make some sense. Third, again, a kind of little mind exercise to try out. Let's try to bracket the modern history of computation. We'll skip the punch card part with the following set of ideas. Let's consider the cognitive meaning, the psychological feeling that we get when we use computers. And let's think of it in terms of here and there, position, space. At the beginning, let's call it, this is actually my 1979 Apple II Plus, still boots today in under a second, still works just as well as it ever did. This, whether it was this or a TRS-80 or a Sinclair ZX80, who remembers that, or whatever it was, this thing was very much here. Now, it's still abstract. It has a very primitive interface. But whatever you do with this machine is literally here. It's literally under your fingertips. And if it isn't there, something's gone horribly wrong, and it's not anywhere. Now, if we zip forward by 25 or 30 years, this is what computers look like. We don't call them computers anymore. I don't think we like computers. We don't like the word computer, so we should think about that for a moment as well. But with this model of computation, and of course we've left out perhaps the most significant part of the ecosystem, which is the smartphone, your stuff essentially is there. It's far from you. It's literally far from you in the sense that it's being handed to you by some server. But it's also cognitively far from you. It's no longer under your fingertips. Now, that's not a bad thing. We're not saying roll back the internet, roll back the web. That's enormous high-value stuff. But something has happened. And we want to explore the cognitive shift that happened when we went from here to there, and what might be gained by taking some of what's there and bringing it back here. And the way I look at it, what's happened, this is actually inaccurate. It should be vacuum around professional computers. So the move from the laptop to this, or the tablet being the dominant paradigm, with a fun touch interface, but let's face it, a less capable interface, that has left a bit of a vacuum around the kind of thing that IBM was so good at inventing, and maybe cognitive is going to bring that back as well. But the UI, a new kind of UI, is also going to be a part of bringing back professional computation. You wouldn't perform finite element analysis to make sure your bridge doesn't fall down on a tablet or a smartphone. You wouldn't plan surgery on a tablet or a smartphone. They're limited tools that have found their niche, but we do need something else. And of course, we can't talk about the history of recent computation without this moment. This was the moment when we went from the command line to iconographic ideas, pictographic ideas about UI. And that started accessing different parts of the human brain. But this is what we've still got today, as I've said already. Fourth, this completes the initial count. This is the legal part of our discussion today. As many of you probably know, Earlier this year, Chief Supreme Court Justices Scalia and Ginsburg made it law that in the United States, when you talk about the future of computation, you must reference Minority Report. And we will not break the law today. I actually, for many, many years, resisted talking about this, but everyone else does, so I feel that I might as well. And there's something else that can be brought to the discussion. Certainly it is true that we invented, for the purpose of the film, a new kind of gestural interface, a domain-specific language, in fact, which was the result of a great deal of research and synthesis, published things like this dictionary or thesaurus, I'm not sure which one it is, training materials so that the actors who, after all, would be seeing nothing on the giant screen on the day would still know the language that they were using, and that a kind of causality could emerge once the effects people had composited in the graphics onto the screen. All of that's true, and we even went so far as to make training videos. At that time, computer graphics modeling and rendering and compositing programs were inexpensive and easily available enough to undertake a kind of prototyping that hadn't happened before. And if you're going to make new UI, it's worth prototyping them through the quickest method that you can. Today, that might actually be code, but in this time, it was easiest to do this. So this was done in 2 weeks for no money, just a lot of coffee and sleeping on friends' sofas. And now the actors and the director and the producers could understand what these scenes could be like. Obviously, they'd look much more professional than that, but this was a critical tool in developing that fictional technology for the film. And that goes on and on. So on the day we came to shoot it, the results have somehow passed into a kind of, into becoming a kind of metric for new computation. Even 12 years on, journalists tend to reference this stuff. And I think that partly it is the causality. It's not made up on the day, which is what usually happens when people try to film gestural computation scenes in future fictional films. The actors knew what they were doing. They were actually the first users of a new system. It just didn't happen to have computation behind it. But they were actually using this new gestural language. But I think there's something else going on here which is not written about and which is not talked about. You're seeing a new kind of user interface, a new radically more capable HMI being a critical part of a time-sensitive process. So these guys have come together to solve a future crime. They need to do it before the crime actually occurs. They've got to sift through mountains of pre-forensic data extracted from the poor psychic teenagers' heads as they dream of violent crime all day, which really is a shame, but at least some good can come of it as you put together tens or hundreds of thousands of individual images and video clips that come out of the kids' heads as dreams happen for you and me, which is to say, asynchronously and without being able to plan or request anything. So this is a UI that is in support of a very dense data-driven process. And this is kind of what we want to move toward. There's a number of other properties here that we'll get to as we go along. So when the film came out, we realized that in a strange sense, we'd actually been able to take a dry run at what might very well become a commercial enterprise or a product that the whole world could use. And in a sense, we'd accidentally conducted the world's largest user focus group test. We'd put this new UI in front of, I don't know, 50 million human sets of eyes, 100 million. I don't know how many people saw the film, but certainly more than read my dissertation, so that's a step forward. And watching audiences watch those scenes was about all it took to convince a bunch of us to come together and form a company in pursuit of these ideas. So this was going to be the third iteration of these ideas. They'd been born, as Zach said, at the MIT Media Lab as a set of obsessions about what UI could become. They'd been purified through the fiery kiln of Hollywood in a strange way, but I would say, looking back, that the kind of simplification that's necessary to get the stuff to read, to be legible on screen, is, is exactly the kind of refinement and simplification you should undertake in preparing a product. So now it was going to be born a third time, and it was going to be born as actual commercial running professional code that as many people as wanted to could use. And the result is a company called Oblong. And what we think of as a spatial operating environment, it's sort of a distributed next generation OS, if you will, called GSpeak. And GSpeak is going to embody a bunch of ideas that we'll explore very rapidly here. So there are now 5 principles that I want to talk about that GSpeak tries to get at. The first harkens back to the title of the talk. We really, really care about space. And the history of computation, notwithstanding the iconographic UI that the Macintosh gave the world, is still fairly abstract. You start with Turing and his cronies, and von Neumann, and they were logicians, they were mathematicians. And because of that, and the biases that brought to the field, and because of the technical limitations, what we got was computers and computer languages that were very abstract, very logical, but do not, as it turns out, partake of space. In fact, they're also missing the temporal dimension. So all of the stuff, where you and I live, is not part of the vocabulary of the machine. And what we want to do is say, what happens if we teach the machine about space? We spend all of our time in space, and we move through space in time. Seems like it's important stuff. Nobel Prize was just given briefly ago to John O'Keefe and some others for discovering back in 1971, or positing and seeming to prove back in 1971, the existence of a place cell, a neuron or a set of neurons or a piece of the brain that's about understanding our place in relation to other artifacts, other people, other architecture, other bits of the environment. And whether those are indeed specialized cells is something we'll have to ask Jeff to disambiguate for us. But there's no question that big chunks of our brain are in fact dedicated to haptics, proprioception, muscle memory, the understanding of where we are in space. And so that's a very kind of literal adjunct to the kind of logical language-based thinking that we're also very good at as humans, and that forms here, to date anyway, the vast majority of what we think of as computers. So what we're going to look at here is a very brief video digest of basic properties of G-Speak systems or spatial computing. Pointing becomes suddenly very simple because we're asserting that every pixel in our world has a three-space coordinate. It's not abstract integer x and y. It is the unique address of that pixel in the room with respect to an origin, which would be Manuela's elevator bank, if I recall correctly. Navigation becomes a very easy thing. The inertia and biomechanics that you're used to manipulating in your own body became the perfect way to fly through two- or three-dimensional space. Touch, of course, is a subset of three-dimensional gesture and spatial computation, but the idea to sift and gather with your hands or to reach out and pull literal or abstract artifacts toward you all gets toward a new kind of meaning. Here we see that sometimes the pixels can move underneath static objects, static virtual objects in space, and sometimes for us the pixels are physical. And all of that should hew to the same gestural language. Navigation in three-space cannot be underestimated. It's critical to be able to fly through a space that depicts something, whether it's literal, again, or some kind of abstract visualization. The last 25 years are a wonderful wealth of computer visualization, but it's only half the story. To be able to move through that with your body, with your eyes, with your mind, is to allow a kind of body wisdom to interact. So we've ended up building very complex systems. This is an oil and gas reservoir simulation front end. There's just some things that you can do with an interface that's more sophisticated than a mouse that you cannot do any other way. And what we're proposing is to drop the mouse, drop that chunk of plastic that makes it not even worth having fingers or hands. Sometimes you don't need gloves. You can work directly with your bare hands and so forth. Now, we don't want to fixate on the gestural stuff. That's one piece of it. But there is something much larger at work here that we'll get to as well in just a second. This is a nice seismic simulation. This is the last 6 years of worldwide seismic activity. Sorted and sortable around a bunch of different axes. And these systems are inherently multi-user, so that's something that happens when you step away from the screen. There's now physical and kind of social space for more than one person to use the computer at the same time. And in a way, that may be the single biggest advantage of working in this fashion. So there's a level of immersion, a level of engagement there that I think you can get some sense of. 2, the idea of agency. We can build, I'm going to assert again, interfaces, computer systems, ways of interacting with data that you perceive viscerally, that feel like skiing or scuba diving or skydiving, that feel like what it must feel like to play an incredibly complicated oboe concerto or guitar lick or whatever it is that activates pieces of the brain that are to do with exhilaration. We can build UIs that activate those same bits of brain, and when we do, when we feel that, we know that we're getting close. So I'm going to show a little clip of a system that we built some years ago, both to exercise some of the new media handling capabilities we were asserting must be at the root of every modern OS. But also, more than anything, this system is a kind of metaphor. And so what it allows you to do is to work through a couple dozen films. They're there in their entirety, every frame. You can zip through them temporarily, but then you can take them apart. Any individual scene, you can grab actors, props, bits of scenery, and so forth, and pull it down onto a kind of composing table in front of you. Then you can move to the next film that was made at a different time in a different country, pull out artifacts and props and actors from that, and start putting together a kind of cinematic heresy. Now, this may or may not be the future of media assembly, but what is important is that the feeling of exhilaration that you get, not through the exertion of raw brute power, but from the kind of fine-grained, sophisticated control that systems like this give you over your own stuff. You should be able to take apart your stuff, put it back together with the same level of dexterity that you could sort through a number of index cards on a table, or work with a puzzle. And another characteristic of these systems that you see here is that they're not limited to one plane or one screen. Stuff can move all over the room. So we're starting to talk about, in a sense, architectural computing. 3, it's not just space. So the title of the talk is becoming an increasingly big fat lie. We need time as well. Time is critically important, but if you think about it, if you program, if you use computer toolkits or programming languages, almost none of them has recourse to expressing either space or time. So they live, again, in a kind of abstract domain. But we have to have time, and what happens when you build systems like that is that you get this. This is a little piece of media running around 5 different screens that are being driven by 3 different computers running 2 operating systems. And the experience, the UI, the content is continuous in space and time across all those screens. This is the future that we have to move toward. It's not enough any longer to say, well, there's just one machine, and artificially, which is the case today, all of the stuff ends at the physical boundaries of the device. All your applications, your data, your communications stops here. The thing has a network, so that's not really necessary, but that's kind of an inbuilt set of assumptions that we've left ourselves with. But we can get out of it as well. This is another sort of exemplar of that same idea. There's a Macintosh, Linux driving a huge screen. We're taking a digital artifact, a little L system tree, pulling it from one to the other using one type of sensor, a prime sense sensor overhead, then coming in to use a much more fine-grained sensor, which is the leap motion detector there, to manipulate the data. So we're moving toward multiplicity, multiple screens, multiple sensors, multiple input modalities. So it's not just one thing. It's not that we're saying that gesture is going to wholesale replace the keyboard and the mouse. The new idea is that you're going to have more than one input modality at the same time, and you'll no more be confused by that than you are by the utensils in your utensil drawer. You don't pick up a ladle to try to eat a steak, right? You know how to do that. It's built into the way our hands and our bodies and our eyes and our senses understand the world and tools that we build for it. And I can't resist showing this. This is brand new, literally less than 24 hours old. This is a bunch of financial data being explored in a 5-sided hexagon. I'll explain that in a minute. A room that is a kind of immersive environment. And just the idea that you can grab all of the data and pull it around you means that you're exercising both the human visual system and all the stuff to do with proprioception. You're putting together those hemispheres about space and vision, and your opportunity for understanding is I think, not just additively increased, but multiplicatively. 4, I don't normally do this, but in such a delightfully technical audience, I'm going to try it. I've long been a proponent of using more words in computer science. For some reason, most of the languages, most of the ways that we build computer languages and toolkits partake of very little of English or whatever language we happen to use. There's about 12 words like set and get and put, and they're so vastly overloaded that they have no meaning at all. So when a word means something and it means it well and uniquely and is elusive, then keep using it. If not, there are opportunities actually to increase human understanding by exercising more of the language, more of our human language. So that's an opportunity. It isn't much expressed, but I want to take you through a very, very brief tour of what it looks like inside GSpeak. So we want to be able to express all the things that I've been talking about. In GSpeak, this is C++. I apologize for that, but what are you going to do? It has to run fast. there's a scene graph. The scene graph expresses computation. It expresses the relationship between the different objects that will be subject to computation. Time is built into this language, language built atop C++ in a basic way. So we talk about the program's respiration at some predetermined rate, might be 60 times a second, 100 times a second, once a second. Every object in the system respires. It inhales, which is sort of a preparatory setup step. It travails, that's where you do work. And it exhales, that's where you perform cleanup. And the idea that all of the objects in the system have this kind of rhythm, this kind of temporal nature, and that it's all synchronized allows you to express new ideas and allows you to build new kinds of interactive systems. You can tell it how fast to respire there. You see one respire every 5 seconds, it looks like. You can build other objects like triggers that sit around and wait until some amount of time has passed or until you reach some time mark and then some bit of execution is put in place. Now, of course, it's possible to do all of this with any language today, but you have to do a lot of explicit work in order to get this kind of behavior. The goal here is to make implicitly available all of those techniques so that you don't have to think about it, so that what you write as a programmer is what you mean at a high level. You can, in fact, even through a mechanism called atmospheres, you can introspect the call stack, so you can see where computation has been. It's incredibly useful to be able to ratchet back up through the stack and find out where you came from, a basic question for all of us humans. And geometry, here's our space. So space is built in at the lowest level. 3 space, not 2-dimensional space, but 3 space. So we've got vectors. It's the only place where we overload the C++ operators. We let math be math. Why should math be such a third-class citizen in computer science? Why must we have com.sun.java.math.cosine? That seems a little bit unfair, doesn't it? Here we foreground it. We foreground the geometry. We foreground the math. And every physical construct in the system, the feld is the kind of abstract version of a screen, but it has literal pixels, is denoted in 3 space with respect, again, to some origin. So it has a physical position. It also has a physical over. It's not always x that increases to the right. If this was x increasing to the right, what's this? Right? So if you've ever programmed in any kind of graphical toolkit, the pixel up there is typically called 0, 0. So that's 0, 0. If you're really lucky, 0, 0 is down here, but you're usually not. That's 0, 0. Here's a second screen. What's the top left pixel here called? Well, also 0, 0, right? Again, we need to assign to each of those pixels its actual coordinate in real-world space. And so flat structures have an orientation, they have a normal, and so forth. We can describe them using these geometric concepts, which are easy, and then the math allows you to get a lot of work done quickly. And then there's the soft formalism, the idea that some bits of computation you want to set up once and allow to run. So colors, positions, various other temporal artifacts can be set up as soft, a soft float, for example, and then it runs. And you don't have to ever perform the computation to get the sine wave out. You just use that variable, and it's been updated. That itself also provides, and you can then network together those softs into more complex computations, and thereby derive a lot of sophisticated visual and geometric behavior. And finally, as we've been suggesting, right, this world is not going to run on a single computer. It's going to extend onto as many CPUs, maybe running heterogeneous architectures to drive as many screens as may be required for the task. And these federations of screens and CPUs may be dynamic. They may come and go. And so what we need is a mechanism for synchronizing program state, program understanding, input paths, and so forth. For that, we've devised a nifty little kind of message-passing, multi-point of contact, rewindable networking scheme that we call Plasma. And Plasma messages are called proteins. And they're highly structured but self-describing and allow you to express in any language, because we have bindings for all major modern languages, these ideas. You agglomerate them into proteins. The proteins are dropped into what we call a pool, and it's multi-point of contact. So n different objects or programs can participate in the pool. So it's not point-to-point. We're finally getting rid of that 1890s style telegraphy idea about what happens when you connect It's more of a biological theme, in fact, just like endocrinology, right? If a bit of brain or an organ wants to signal some other part of the body, an endocrine is placed into the bloodstream, it travels around, the signal is accomplished, but evolution sees to it that other organs or other pieces of anatomy that may be interested in that signal can take it up as well. So it's a multi-point of contact, multi-participatory system, and the only property that a pool has is that it's ordered. Everybody puts proteins in. We're not going to say whose goes in first, but there's a fixed order, and all the programs get proteins out in that same order. It's rewindable, too. So if the n+1st machine joins the tribe that are working together to produce some application or some UI, and it doesn't know what the state is, it can rewind the pool until it's gone far enough back in time to accumulate enough context, enough state to understand where things lie. And we call the process of dissecting and understanding what's contained in the proteins, metabolizing them, which you see there. So that's enough of that. I'm going to get to the final point, which again may be the most important thing of all. We want to emerge into an era of plurality. And to do that, let's do one final exercise. I'm going to propose a weird operator, a kind of human operator, a mathematical operator, I don't know what it is, called hoist. And hoist is what happened when we went from the command line interface to the GUI. And what I mean by that is as follows. So if you think about using a command line only system, you might boot up VisiCalc, right? So you might work in a spreadsheet for a moment. If now you're interested in composing some text, you have to shut down VisiCalc. You have to shut down the spreadsheet in order to boot up the word processing program. And if email had even existed at the time, you'd have to shut down the word processing program to start up your email system. That makes sense in that world that is lit only by the command line. But something magical happens when the GUI lets us have overlapping windows. Suddenly, multiple processes can run at the same time. And now, excuse me, we have a cognitive way to do all those things at the same time. You can edit your spreadsheet. You can drag the contents of the spreadsheet, maybe highlight some cells, drag it into the middle of a text document. And then you can take that thing and dump it into email and send it. So something has happened. Something that was linear has become nonlinear. Something that was singular has become plural and parallel. The question now, and interestingly, if we think about what happens here, we went backwards. Right? This only runs one program at a time, so we've very much lost that capability, which is fine as long as we don't only have these. The question now is what happens if we take the GUI and apply the hoist operator to it. And I'm going to propose that what happens is that you get a kind of higher level system, a shared pixel workspace in which multiple people can work, in which maybe multiple individual devices can participate as chunks of pixels, as operating, running code, and in which a plurality of inputs is possible. Not just one person using one mouse at a time, but one person using a mouse, someone else using a pointer, someone else using gestures, someone else using a tablet or touch input, all of that making cognitive sense. And so a system like this, which Oblong builds, is an early suggestion of that kind of work. So here's a room. Again, this is a kind of architectural computer in which many of the walls are filled with screens, lots of pixels. More pixels means more possibility of information. It's a shared environment, so everyone's looking at the same stuff. So right away, you've got the advantage of shared visual context among humans. And we've got lots and lots of different mechanisms for input. This woman here is using a tablet. That makes her a first-class citizen of this experience. She can manipulate the workspace. She can upload content into it. And once the content's there, she's actually dropped the tablet and is using this spatial wand to more adroitly move content around the system. So every device in the room should and can make you a participant in a system like this. Again, we're not saying the new technology is great, it's better, drop all the old technology. People have tech that they like. People have devices that they're very good at. And so there's a kind of inclusive approach to this kind of work that is critically important. Bring whatever you brought with you into the room out and use it, but use it in this kind of participatory way. You see that telepresence and VTC type work becomes a piece of the entire fabric, but not the whole of it. Here we've plugged in a laptop, and so one person's tool is now available visually to everyone else in the room. whiteboard is a perfectly good piece of meeting room equipment. There's no reason to feel that we have to go stampeding off and make that fully digital. What we need is a way to make all of the content that's generated there become a first-class citizen in the workspace. And you can simply point the wand at the whiteboard, click, an image of it is imported, or a live stream of it is imported into the system. So navigation, content injection, manipulation, all of it happens in parallel for multiple people working in the same room. And then you can start to join rooms together. So I'm going to propose that an environment something like this is going to become the necessary front end for cognitive environments and sort of next generation computation. You need something that's this rich. You need something that's this participatory, where everyone has the same context, and that allows people to work at the same time. To lean on an architectural analogy, can you imagine a magnificent building like this that is for some reason single occupancy? None of you can come into this building if John Kelly's already in this building. That's nonsensical, right? Or a building like this that's single use. If we're using the spectrophotometer, the coffee maker doesn't work. But those are the computational systems that we build today. And what we want is to have computational systems, digital systems, that work like real architecture. Architecture that people build for people, that people build to contain human activity, that partake of the kind of spatial understanding that we're all experts at, having been born into the universe. And so this is the kind of stuff that we should be building. What we want is to drive toward a future in which we can build systems that are about human attention rather than human distraction, that capture human intent and do so on human terms rather than trying to project your consciousness into the rather more limited and abstract world of the machine, which I'll claim is a little bit of what we do today, that really are about meaning, again, human meaning, and what's important. And that, more than anything, are spaces for synthesis, that are not just spaces for entertainment, but that are places that are as rich as the physical world is when you pick up a pencil or a pen or a paintbrush, that allow and invite the expression of human intent, and that are essentially transducers for human will. These are the systems that we need to build, and more than anything, these are human systems. Thank you.
Ad hoc. So this is all ad hoc computing. Yeah. Okay, we've got time for a couple of questions.
Great.
Thanks, John.
Sure.
Again, let's start maybe up at the top. Right here. Can you see okay? This gentleman here.
Great.
Thank you for that. That was really terrific. It's just a simple question. In your examples in the different platforms, I just noticed that I didn't see a lot of smartphones. Mm-hmm. So I was just curious if you could talk to that platform and the interaction on that platform. What its challenges might be, or is it as near term as some of the other platforms that you were showing?
There were at least two videos in which we caught a brief glimpse of the smartphone being used. There was one little game-like illustration where you had three people using their phones and the inertials inside them to generate pointers on the screen all at the same time. And then in the second case, in that last video, we saw the smartphone's camera being used as a kind of data source, an image capture and injection source. Phones are great. We now know exactly what they're good at, and we're rather more laconic about what they're not good at, but that's implicit. What we can do is say that all the things that they're already good at will remain, and in addition, as the sensors get better and better, we can use them as pointers. We can use them to capture bits of the physical world or the digital world, and then transmit that into a larger shared workspace. So I think the applicability of these will not go down. It'll go up. And so the question really is, what's the meaning of this thing when it can interoperate with other sets of pixels? There's no reason in the world that I shouldn't be able to walk into this room, maybe composing some text or reviewing a document here, or even doing some kind of synthetic work, and just by dint of proximity to this larger area of very rich, delightful pixels, have this computation extend pseudopod-like onto the screen. That's what interoperable pixels should allow, and that's what systems like the ones that we build are trying to offer the world. And of course, that applies not just to smartphones, but every other device that people already have in their lives.
I want to get some new questions, Bob. We'll hold on for just a minute. Others over here? Over here. Yeah. Peter?
The environment you described is a pretty specialized environment, meaning that if you want to build one of those things, you need to have some resources to build such things, right? Compared to having it in your home, which is not easy to do, right? So there are cultural aspects of how easily you can propagate these ideas to a broad audience because they're limited by resources. So do you have any ideas of culturally what you have to deal with to propagate this?
Did everyone hear that? The question was about, the assertion is that these are very specialized environments, and how do we get them to go everywhere? I'd actually claim that they can be specialized. You can build big five-sided immersion rooms, but that's not what we're after. What we're after is essentially protocol level. We want every device and every chunk of pixels to be interoperable, and so that federations of those devices and CPUs and computation and pixel spaces can happen when they need to, and to whatever extent of richness is afforded by the pieces that you have. So, de facto, that should be able to work at your home, even if you don't have an expensive motion tracking system. You've still got your phone, you've got your TV, you probably have 5 to 15 computational devices in your immediate surround. All that stuff should work together. So that's really the message. It's about everything working together in a harmonious fashion, and not about any particular modality or space.
John, let me, as a follow-up to Peter's question, let me ask you, how have you thought about ad hoc environments where people are coming and exiting and sensors are joining and being removed from, and you've got multi-level sort of access to this? What's that environment going to look like 5 years from now?
There's a lot of aspects to that question. There's a privacy aspect, right? If these pixels can become anyone's,
Yep.
How do we assure that shenanigans don't, transpire and so forth? And there's a lot more,
Assuming everybody's honorable.
Assuming everyone's honorable. The piece of that I'm personally most interested in is the extensions to the UI and to the kind of visual signaling mechanisms that'll have to take place for people to understand these new environments. Right now, what you get is a little mouse, a cursor, right? A little fly that creeps around your screen. We'll need something much richer. And I think that one of the mistakes that UI designers have made over the years is to go for this kind of platonic standoffishness, where the less that's revealed about the computational processes, the better, right? We sort of pretend as UI designers that whatever it is working perfectly, and you don't need to know. On the contrary, I think that if we reveal a little bit of the processes that are happening in the background to the users, I should say, through a new language that will have to be invented, that we're working on, but it'll have to be a joint effort and will have to be standardized, that actually can increase the bandwidth between the human and the machine. You've got some idea of what it's up to and why it's making decisions that it's making, and when it gets stuff wrong, why it gets stuff wrong. So there will be needs for, let's say, a new kind of peripheral vision. There will have to be something that happens over here if a new device has come into the space that might want to participate on the screen or in these pixels. I'm sort of making that up, but that flavor of new design technology is going to be required for us to be able to understand and make maximum use of these systems. We can do it. We've got all the pieces. What's required is some real design.
John, thank you very much. Terrific.
Thanks.